So two of the big takeaways is moment of inertia is about how the object is shaped and the way in which you spin it. Now, I don't want to say that mass doesn't play any role. What I want to emphasize is that there might be something more important than mass. So that's where I wanted to kind of leave us yesterday. And we did some demonstrations to to show that. Also, in the course of those demonstrations and in the course of statics, we talked about an analogy, kind of a way that we could probably predict what things that have to do with rotation might look like. What I mean by that is, I was hoping that by the end of the day yesterday, it wouldn't be too big a surprise for you to rewrite Newton's second law, but write it for things that are being spun as opposed to things that are being moved from one place to another. And we talked about that yesterday as well. Do you think you could do that for other things? Like, we know that kinetic energy is 1/2 mv squared. What do you think that might look like for something that spins? If you're just to try and, I don't know, guess? Go ahead. Okay, so I think I would replace the velocity with angular velocity. What else? Go ahead.
Mass with torque.
I don't think mass with torque, but I think mass with moment of inertia. So there'd be, wherever I see an M, maybe put an I. And I still think the 1/2 might be there. I mean, there seems to be a lot of symmetry in physics, so this doesn't seem too far-fetched. How about, and we'll just put rotational kinetic energy. And that is the formula for rotational kinetic energy. It's 1/2 I omega squared. Now, what do you think with momentum? Momentum is, mass times velocity. What do you think it might look like if we were to predict what the angular momentum of an object was? What's that? Yeah. So angular momentum, if the symmetry persists, would be I times omega. All of those are true. So when we talk about moment of inertia, it's going to be important because it appears in a lot of places. Does that make sense? There's also angular work. I mean, if we talk about work being force times displacement, what do you think angular work would look like? If we're trying to continue down this, it'd be torque. What's the angular version of displacement? Yeah, delta theta. Yeah. So all of these things that we've already kind of talked about, I won't say learned. Yesterday we learned a lesson, didn't we? That maybe with stuff from first semester we haven't really learned all the way. But it's all applicable here. And there's always going to be a similar angular thing to a linear thing. Now, what I would really like to do today, and it's going to take the entire class period, and I think it's worth it, you may not. I want to kind of prove to you what moment of inertia is. I'll only do it once, and once we're done with it, you'll have notes here. I won't ask for this specifically on a test, but there's going to be pieces of this that I think you'll find you will use a couple of times throughout the course of this unit, and you'll be happy that you know it. But it's also because, about this just a minute ago. Now imagine that that blue piece of tape is actually a piece of the disk, that I could carve out a little cube of this disk. And let's say that that cube has mass m. If I carve out just that cube and then put it back in place, at this moment, that cube would have a kinetic energy of 1/2 mv squared. That would be the kinetic energy of that one cube. Because remember, energy doesn't have direction, and because it doesn't have direction, it's just how fast the object is going. Now, I know in my head that how fast that object is going is dependent upon how far away that cube is from the center. In fact, I might mark this as just being velocity 1, because I could carve out a different cube. Maybe a cube that is the same size, but I could carve out another cube and say I carve out this cube. Well, that cube is a different distance away from the center. So if I put that cube back in place and I keep spinning the object, wouldn't that cube have a kinetic energy that would be different than the first cube? Right? Because the velocity would be different. Cube number 2 is closer to the center, so its velocity would be less because it's not spinning as fast. That piece isn't moving as fast. Everybody okay with this so far? Any question about what I've done so far? Now you understand I could carve out lots of different cubes if I wanted. All right, cube number 3, closer even still, moving the slowest of all the cubes that I've talked about. And this cube would have kinetic energy equal to 1/2 mv3 squared. Now I've only carved out 3 cubes, but if I wanted the kinetic energy of the entire thing, I would have to do this for every single cube. Does that make sense? Because the whole thing is spinning, but every piece is spinning at a different speed. So if I want to figure out what the kinetic energy is, I might have to look at all of these cubes. But if I did that for every single cube, I could add all that up, and that would be the total kinetic energy. Now, I know we just talked. I'm trying to prove this to you, okay? I'm trying to give you ample evidence. Now, there's something unfortunate here, and it's a lack of something that you know. And so to put this in perspective, or at least to put this appropriately, if I wanted to do this, the total kinetic energy, I don't want to write the word out 1,000 times, so can I just write T, K, and E, that's total kinetic energy? That would equal 1/2 mv1 squared plus 1/2 mv2 squared plus, and I'd have to add that up forever. There's a way to write this. It's symbology, and I don't know if you know it or not. I've used the symbol before. It's the summation symbol. Have you seen this before? So the summation symbol is a way to say, do this. Add the same thing over and over again, but change it in some small way. So the way you use this, if you're unfamiliar, is to put some stuff around the top and bottom of the summation system symbol to tell you what to do. For example, you say, I'm going to call each of the items by name. I'm going to number, or by number. I'm going to number them all. For each item, they will have a velocity and a mass. So each item in my object, or in my sum, is going to have a mass and is going to have a velocity. I'm going to start with item number 1, and I'm going to end with the last item. Now, right now, I don't know how many items that is. I don't know how many squares I would have to take out to get the whole disk. So we use n as just a reminder to make sure you get to the last one. And it tells you the formula you would have to use to figure out the total kinetic energy. This is a summation. And this is how we use a summation to kind of tell us stuff about an object. Now, like any summation, this summation is the same thing over and over again. Now, one of the things I changed, as you know, is I put a little I on the mass. Because I'm thinking, if I was actually carving pieces out, they might not all be the exact same size. So I'm going to assume that maybe each piece is a different mass. just in case. But I can also use the rules of algebra here. What I mean by that is, can you kind of realize that every single piece of mass is going to have a 1/2 out front? Well, the rules of algebra say if I have the same term in a polynomial, I can just factor that term out. Well, I can do that in a summation as well. I mean, I can take and factor out the 1/2 and still say that I'm doing a summation, but at the end, just take my sum and multiply by 1/2 rather than multiplying by 1/2 for every single object. Does that make sense? Now you might ask, okay, I see you're doing stuff here, you're writing things, Mr. Sheldon, but I don't get where you're going. Well, I said something at the beginning of this that I think is important. Every one of these velocities depends on where the piece is, right? Piece number 1 was here. It had the biggest velocity. Piece number 2 was here. It had the next biggest velocity. And piece number 3 was here. It had the smallest velocity. Is that true? Well, all of those velocities are based on something you already know. Those velocities equal the angular speed times r. The whole disk has the same angular speed. So for this one, v1 is going to equal the angular speed times r1. And for this piece, v2 would be the angular speed times r2. And for piece 3, well, the linear speed would be the angular speed times r3. Well, I can see it. What's your point? Here's my point. I could rewrite this as 1/2, put my symbol in here, mi, but replace v with omega times ri. Wouldn't that accomplish the same thing? No. The reason I want to do that is omega is the same for all of the pieces. This way I don't have to calculate all the individual velocities. I can just calculate how far they are and multiply the whole thing by the angular speed at the end. Does that make sense? In fact, if you look closely at that, omega is the same for all of them. I could go ahead right now and factor it out. In fact, that's what I'm going to do. I'm going to factor it out. I know I'm factoring out on the other side, but that should be okay, right? So I can do it in any order I want. Now, this isn't a lot of evidence. There's a little bit of evidence, but do you see in here the shadow of 1/2 times I times omega squared? Do you see that in here? If that's true, if I want to prove that it's true, I'm suggesting that this is how you calculate I. In fact, what I'd be saying is I equals a sum a way to calculate the moment of inertia. Now, you don't have to believe me, but you do see that clearly there's some similarity here, don't you? Same structure and everything, the 1/2s and the omegas, all that shows up. That's not evidence, that's not fact, but it just looks too close to not be possible. Now, I think we can test it, but I also want to point out something here. What we said was yesterday that the mass may matter, but where the object is relative to the axis of rotation matters more. Right? Isn't that what we said yesterday? Isn't that what we showed yesterday? Isn't that what this says? It says the mass matters, but look, how far away? R is the distance from the axis of rotation to where each cube of mass was, right? That is the distance away from the axis of rotation. and it's squared. Doesn't that seem like that makes it more important? If I double how far away a piece is, that piece is 4 times more important because it'd be 2 squared. So suddenly I have something that seems to match up with our experience. But this isn't evidence. This is just me presenting you with what looks to be like good similarities. So what I'd like to do is see maybe if we can figure out if this is true or not. All right? Does this really stand for what we see with our objects? So I want to provide us with a way to do that, a way to provide some evidence. And I think I can prove 2 things at once, kind of. I said to you that the moment of inertia about the end of a long rod is, well, what is it? You guys should know, right? You're supposed to memorize it. Haven't done that yet? That's about the middle, so pretty good. It's 1/3 ml squared. Okay? So I want to see if our formula would produce 1/3 ml squared. And I want to use the meter stick as the model. Is that okay with you guys? Now, I'm not really going to use a meter stick as the model. I'm using it because the meter stick has on it something that I think you will find visually helpful. It's got marks on it, and they're placed in a regular and repeating way. You guys see that? I'm going to say that this rod is mass capital M and is length L. And the reason is I don't want to put 1. If I use a meter stick, then the L becomes 1, and we kind of lose some of the nuance by the end. Does that make sense? So I'm going to put L in there. Now, my formula for moment of inertia says to start at piece 1 and go to piece n and add up the mass of each piece times how far away each piece is from the axis of rotation. I suggest we take our meter stick up and break it into 10 equal pieces and treat each piece like a piece of mass. Now, I don't want you to physically break the meter sticks. I want to mentally do this because I want to see if we can figure out a way to do this. Now, if it were me and I were trying to take good notes, you have lines on your paper. You might want to turn your paper sideways to do what I'm about to do, but I'm going to try and break this up into 10 pieces by carefully drawing lines and try and make it look like they're 10 equal pieces. I think I did okay. Not great, but okay. But you have the blue lines, so you can make it perfect. Now, the first thing I'm gonna say after I've drawn this out is I'm gonna make some assumptions. Now, I think these assumptions make sense, but you may not. So let me help you out. If I break this up into 10 pieces, each piece would be about this big on a meter stick, right? I'm going to make the assumption that the center of mass of each piece is at the center of the piece. Does that make sense? You guys see what I'm doing? I'm going to say right here at the center is where the mass is concentrated. That would mean that at the center of each piece is where the center of mass is for each piece. Now, there's a total of 10 pieces, but if I break it up into evenly sized pieces, wouldn't the mass of one piece be 1/10 the mass of the whole thing? Does that make reasonable sense? Okay so far? All right, we're going to build a summation. We're going to start at piece number 1 and write out the term for a couple of our pieces. Does that make sense so far? What we're going to do? For example, here's what I'm going to do. Piece number 1, it has a mass of 1/10 the mass of the whole thing. And R1 has to be the distance from the axis of rotation to where the first center of mass is. So that's from here to here. How much of L is that? And you have your meter stick. Wouldn't that be at the 5 centimeter mark? And so the whole thing's 100. 5 over 100 is 1/20th, right? Wouldn't this be 1/20th of the way? Does that make sense? So I'm going to put 1/20th of L there. And that whole thing is squared. That's term number 1. How many of these terms are there going to be? What's that? How many pieces are there? 10 pieces. I expect there to be 10 terms. 1 for each piece of the meter stick. We're adding them all together. So let's go to the next piece. What's the mass of the next piece? Yeah, still 1/10 of m. Each piece is the same size. What's R for the next piece? It's from here to here. How far is that? You have your meter stick. Can you figure it out by looking at your meter stick? It's going to be the middle here. How many 5s is that? 3. Isn't it 3? So instead of 1/20th, this will be 3/20ths, right? Because it's 3 5s to get here. You're looking weird at me, but this is how far, this is where the first one was, right? You have a meter stick. You can look at yours. The next middle point's got to be at 15, doesn't it? 15 compared to 100 is 3/20ths. Look, I'm not trying to make this tough. You guys see this okay? Now, before I go any further, because there's going to be 10 of these, can you find anything here that's probably going to be in every single term? Okay, so 1/10 m, definitely going to be in every term. Anything else that's going to be in every term? What's that? L squared, right? Isn't L squared going to be in every single term? Can we just pull those out front and be left with the rest of it? Is that all okay with you guys? Now, this makes sense because I think our answer is going to have something to do with ml squared. That seems pretty reasonable, right? Now it's just whatever we get inside this thing. And we already know the first one is 1/20th squared plus 3/20ths squared. Let's go to the next center. How far is the next center from the axis of rotation? How many 5s is it? 5/20ths, isn't it? It's 5 of them. We're at the 25 centimeter mark now, right? So 5/20ths. Now, I see a pattern developing. Do you see a pattern developing? If you actually do this stuff, and this used to be part of Algebra 2 called recursive formulas and finding patterns in numbers. I think it's gone now. I don't think you guys learn any of this crap, which is too bad. Ooh. Oh, good. So I will write it all out because I like to be a completionist, and that's a character flaw. But you guys, I hope, are already way ahead of me and are starting to work this out. Now, you guys didn't say it, which I'm a little sad about, but we could have factored out the 20, right? It's not too late. Are you okay with maybe, what did I just do? Oh, you gotta be kidding me. Oh, man. I'm so frustrated. The worst part is it's in the video now this way. And I thought this one was going okay, but I don't know, my videos are stupid. I don't know why anybody watches them. Totally is, but you don't know how to do recursive formulas, so there's not an easier way. But I am going to do this with you guys. I'm not going to do it the way you're doing it. I am certainly going to factor out that 20 because 20 squared is 400. So I'm factoring out the 20. And that's going to give me with 1 over 4,000 out here. And then the inside is just going to be all the squares. That's how I'm going to do it. You can do 1 over 20 and then square it, but that seems like a lot of extra work. So I took out the 20. And that's going to be 1 plus 3 squared plus 5 squared plus 7 squared plus 9 squared plus 11 squared plus 13 squared plus 15 squared, and that's the last one I know. All right, those are all the squares. Did you guys get that too? And now we have to add them all up. So I'm going to add them all up. And I suggest a couple of you do this to keep me straight. So 361 plus 289 plus 225 plus 169 plus 121 plus 81 plus 49 plus 25 plus 9 plus 1. I got 1330. Did you guys get that too? Okay. Now, I know if you get to where I am, this does not look like this. I know it doesn't. But do me a favor. You already know that 1 over 3 is 0.3 repeating, right? You know that? Like if you did in your calculator right now, did 1 divided by 3, you'd get like a bunch of 3s. What is 1330 divided by 4,000? I got 0.3325, which is 0.333 times ml squared. I know 1330 isn't over 4,000 isn't 1/3. Is it close to 1/3? I'd say it's close. Now, one of the little details is this is a sum. You're adding pieces together. So moments of inertia add together. If you have multiple pieces of an object, you can add the pieces together to form one object. Take and find a way to break that thing up into lots of little pieces and add it up, right?
Good morning.
So I know that this will be difficult, so just hang on for just a minute and you'll kind of see. It's not uncommon for a spacecraft to have a shape that looks maybe something like this. Now, part of the reason for the look is, you want to have something that has all of your delicate electronics in an easily to encapsulate package, but you're probably going to want to have something that you can open up so that you can collect solar energy and dissipate heat. So you'll have something that looks like this. Well, if this has to be spun, which oftentimes you might want to spin this because when you spin something, it tends to stay spinning. That's the whole point. This is a set of objects, isn't it? This looks like a rod spun about its middle, or about its end. This looks like a rod being spun about its end. And this whole thing looks like a disc being spun about its end. Well, if you know what the moment of inertia of a disc is, and you know what the moment of inertia of a rod is, you can add together the moments of inertia. And by doing so, get an idea for what the moment of inertia of the whole thing will be. Moments of inertia add together. Now, there's a problem, and I need to handle that problem before we go on, and I have 9 minutes to handle that problem, okay? Here's the problem. I want you to imagine something you don't want to have to... Okay, so like this. Imagine I do have a rod, and we're going to spin it about its center. But imagine that this rod is actually one of them old, like, silly cartoon versions of a dumbbell and has 2 spheres on either end. You guys know what I'm talking about from like old cartoons and such? So something like Bugs Bunny might be working out with. Nowadays we wouldn't, but back in the day perhaps. So if I bring this up because let's imagine I am mounting these spheres to the end of this rod. Can you imagine that? So the rod is, say, L wide, and the spheres have a radius of, say, R. All good? I'm just making up some stuff real quick. We can say these are the mass of the spheres, and this is the mass of the rod, mass of the spheres. If I wanted to spin this about the middle, I would need to know the moment of inertia of the spheres and the moment of inertia of the rod, and I do know those things, don't I? I know the moment of inertia of a rod about its center is 1/12 ml squared. Is that good? And I know the moment of inertia of a sphere, solid sphere, by the way. You're supposed to have memorized it. Do you know it yet? So we'll say not yet. 2/5 mr squared. How many spheres are there? How many rods are there? Could add those things together, except for one problem. And we have to handle the problem right now, this minute. The equation I gave you was for spinning the sphere about its middle. Are we spinning the sphere about its middle? No, in fact, we're spinning the sphere about something way over here, right? I think that's going to increase its moment of inertia because we have increased the distance away the mass is from the axis of rotation. Now, there's a way to do it, and I want you to have it in your notes. You don't have to do this every time. Once you have found a moment of inertia, you've actually found a lot of them because there's this thing, and you have to know this. It's called the parallel axis theorem. All right, so it's called the parallel axis theorem, and it says that you can shift the axis of rotation to any parallel axis you want. Put the word parallel in there, because it can't do perpendicular axes, only parallel axes. You can shift it to any parallel axis you want. We're on a weird schedule today, aren't we? Okay. We'll talk about this tomorrow. We didn't get quite as far as I wanted today, but we did pretty good. Good day.